Okay, so now we have our second speaker of the day, Jose Correa. So Jose is teaching at the PhD program. So he's teaching this week, and his lecture is about profit inequalities. So and the talk is also about profit inequalities. So Jose, I know Jose since at least 20 years, 25 years, perhaps more. So we met the first time he was undergrad student. He was doing an internship at the École Polytechnique in Paris. Then, so he's from Chile. Then he did his PhD at MIT. Then he, with probability 1, he wanted to come back to his home country, which he did. He's one of the most prominent people I know, perhaps multidisciplinary, because he started in operation research and optimization, but now he's one of the leaders in algorithmic game theory and probability, like the talk today. And we are very proud and happy that he's collaborating with us and coming back to Morocco again.
Thank you, Rida, for the nice introduction. Okay, so I will try to give like an overview talk on this topic that's called profit inequalities. That is basically about online decision making. And so I want to first, I mean, the students in my course know what profit inequalities are, but many people don't know, I assume. So I will first like define the simplest model, and then my goal will be to like describe a few proof ideas and how these proof ideas extend to other models. So it's mostly an overview talk, and by the end of the talk, I will tell you a little bit about a new proof idea that came up from collaboration with Reda and Rida here out of my course last year. I proposed some problem, Reda took it and made some very interesting progress. Sorry? Reda. You are Rida. For me, you are Reda, you are Rida. I mean, I know for you guys it's the same, but for us. Sorry? Well, but the way they write it down is not the same. Okay, so I know in Arabic it's the same. Yeah. Anyhow, so let's start. So what is the profit inequality first? So it's a very simple online decision-making model that was born in the late 70s. So in the late 70s, people were like secretary problems and many other online decision-making problems were posed. And this was one of them. And the basic model is as follows. So suppose I have one ticket that I want to assign, and I have a sequence of agents with independent valuations, random valuations. We know the distributions of all the valuations. So we have valuations VI that are distributed according to FI, each of them. And the agents arrive in this sequence. We observe the realizations of these valuations one after the other. So we first observe V1, then V2, and so on. And upon observing evaluation, we must decide whether to allocate the item or not. Okay, so we see V1, and we decide whether we give the item the ticket. Let's say this is the ticket for tomorrow's semifinal. So we have to decide whether we allocate the item to this first person that came, or just let her go and wait for the next agent to come. The goal is to maximize the expected valuation of the person getting the item, which is essentially the social welfare of the allocation. This is really the goal. And the special thing about it is that instead of, just solving this problem, it might be interesting or not, I don't know, but what we want is to understand what is the loss that we have because of the fact that we have to work online. So basically, we want to compare our solution, the expected value of our allocation, against a profit. And what does the profit do? And this is the term profit inequality comes from this profit. The profit can actually see all the valuations beforehand and just picks the maximum. Okay? So we want to compare the expectation of what we get, of what our online algorithm gets, to the expectation of the maximum valuation. Okay, so this is the profit inequality problem, the basic one. And where is my clicker? Okay, so the online optimum is actually very easy to compute. It's like a very simple dynamic program. So you compute the expected value of the future, which we can call, let's say we are standing at time 1. The expected value of the future is the value we would get if we have V2 up to Vn. These are the random variables. We look at the current value, V1, which we know the realization, and we take the maximum of the two. So if V1 is bigger than the future, we take it, otherwise we continue. Okay, and we can compute this by backwards induction. Good, so this is the optimal algorithm. The problem is that analyzing this and comparing this with the profit is typically not so easy. So the classic result here from Krengel and Sucheston is that the value we can get in this online, by the optimal online algorithm, is at least 1/2 of the expectation of the maximum. So this result is known as the profit inequality. So I could stop my talk here, but it would be a bit short. It's a bit boring, no? And the other observation that is also very old is that this 1/2 here is best possible. We cannot put any number which is bigger than 1/2 here. Okay? So why is this? I mean, there is a very simple instance, which is this one. Let's say there are only 2 agents. The first agent has a deterministic valuation equal to 1, and the second agent has this long shot. So this random variable that takes a huge value with a tiny probability, and 0 otherwise. So the key observation is that the expectation of V2 is 1. Therefore, when you play online and see the first valuation, you see a 1. You compare against the future, is also a 1. You are indifferent, so you say you stop. So your valuation, the value that the decision maker, the online decision maker, will get is 1. But the expectation of the maximum, so the profit, will first actually see this random variable. With probability epsilon, it will get 1 over epsilon, so 1. And with probability 1 minus epsilon, it will take the second one. So another 1. 1 minus epsilon. So it's going to be 2 minus epsilon. For epsilon, epsilon is arbitrarily small. The ratio is 1/2, the ratio between these two things. So it's clear that we cannot put anything, we cannot put 0.51 here in this theorem. So
excuse me, but this example also kind of artificial because unboundedness of utility.
no, that's for every fixed epsilon, this is fine, right? So if you want to put anything bigger than 1/2, I can find an epsilon in which this will be violated, right? I mean, if you impose more conditions on the random variables, well, fine, then maybe you can improve the 1/2.
But it still will be fine.
What is the constant if it's ID?
Okay, so if that's also solved. This, if it's IID, this is much better. This is like almost 3/4.
So just to answer somehow.
Yeah.
But I think he asked, even if it's bounded, we still cannot base 1/2.
Yeah.
Cannot be.
We cannot base because the one we will have epsilon in V of V1 and
Yeah, you can scale down the instance also, and then.
I'm saying whenever the maximum of VI and minimum VI somehow bound.
Yeah, then you can definitely get some constant, some bound that will depend on the bounds that you are imposing. But this, like,
Distribution can be bounded. You're thinking about any possible distribution with any support, but assume F comes from some bounded distribution where you have.
I mean, if 0 is in the support, then you have the same problem.
The support, I understand.
Then you will have the same problem because you scale everything down. Right. All right, so there are many proofs of this result. So there is one proof involving induction over the optimal algorithm. There is a very nice proof by Samuel Kahn from '84 that actually sets a single threshold. So you find one price And then you assign the item to the first agent whose valuation is above the price. And then this price, there are like several versions of this price that works. One is the median. We'll see some of these. One is the half of the expectation of the maximum. Then there is a proof based on online contention resolution, which is a technique that I will try to discuss briefly. And there is even a proof that doesn't use knowledge of the distribution, which is also very interesting. So basically, this proof only needs one sample from each distribution. You take the maximum of the samples as your threshold, and then you play with this threshold. And this also gives 1/2. So all these proofs and different algorithms recover this result, exactly, the best possible result.
What was the first proof? The 77?
The 77 is a threshold base, but it's like they don't explicitly characterize the threshold. It's like they find the supremum of something. Actually, the Krengel and Sucheston proofs gives only 1/4. And then there is some other guy that mentions that their proof can be improved to get the 1/2. Alrighty, so and then these proofs, so the good thing about not all the proofs, but some of these proofs is that they actually extend in different directions. And this is what I want to discuss a little bit. So let's see the first proof, which is, and before I mention this, I mean, it's pretty clear that then this gives rise to a lot of different problems. So first of all, here we're assuming the order is fixed, but in some applications, one can think that the order is just random, or that is even the decision maker can select the order, or some other variants. The information, again, here is, we know the full distribution, but in some situations, we don't have the full distribution, but say we have access to samples or some other statistics about the distributions. Even there are cases in which the information is fully adversarial, so there is an adversary that actually is giving these values. And finally, we will be talking about just selecting a single item, but I will be mentioning that there are many other settings where this makes sense, so selecting a matching in a graph, or a matroid in an independent set, or like online combinatorial auctions, etc. So there are lots of problems, and that's why I think the topic is so popular these days, because there are just lots of problems. Okay, so this is the first proof, and probably still the nicest proof. I mean, this is very transparent, I think. So the proof is the following. So first of all, let's pick a threshold T. Let's pick a threshold T. And for simplicity, I will assume here that all the distributions are continuous, strictly increasing, so there are no ties, never, and everything behaves nicely. And this is not needed, but let's just stay there. And let me call P the probability that the maximum is more than T. So this is the probability that there exists an agent that wants to buy at that price. Okay? And we will take the expectation of the decision maker as the expectation of VR. So R is this random time, which is the time of the first valuation above the threshold. And we'll decompose the value of the allocation as the revenue of the seller plus the utility of the buyer. Okay, so the revenue of the seller is very easy. We're selling at price T with probability of selling P. So the revenue of the seller is just P times T. What is the utility? Well, the utility is the expectation of VR minus T. The person that gets the item minus T. That's all. So what is this expectation? I want to lower bound this expectation now. So the trick here is to just condition on the stopping time. So we will condition that we actually stop at time I, and then multiply by the probability of stopping at that time. And then there are two issues here. One is that this condition, since the VIs are independent and all the random variables, the valuations are independent, the only relevant information in this conditional expectation is that actually VI was bigger than T. The other information this is giving is that all the VJs that came before were smaller than t, and that's why we didn't stop. But those are independent, so we don't care. So the conditional expectation is just the conditional expectation given that Vi is at least t. And the probability of stopping, well, it's just the probability that all these guys were below t and this guy was above t. Right, that's why we didn't stop. And now the trick is that this is essentially the probability that the item is available when I comes. This is exactly that probability, right? It's the probability that I didn't sell before time I. And this we can lower bound by the probability that the item is available at the end of the sequence. So it's just like, we just, instead of taking the product of over guys that are less than I, we take the product over everyone. And this is convenient because of our definition, right, of t. It's convenient because of our definition of t. So now this is 1 minus p, this product, and we can take it outside the sum. And here we just have the expectation of the positive part of Vi minus t. So this conditional expectation times the probability. And now we have positive things. The sum of positive things is more than the maximum of positive things. So we can we find this lower bound of 1 minus p times the expectation of the maximum of Vi minus t, the positive part of these things. Good, so now we have the revenue is, our bound is pt, and the utility, that's our lower bound. So we lower bound the expectation of VR, right, of the decision maker. So now we are done, essentially, because now once we have this lower bound, which is called like the balance prices lower bound, we basically just plug, we take out the positive part from there. It's another lower bound. And now we can choose t. And now if you think about it briefly, if you choose t such that p is 1/2, so we choose the median of the expectation of the maximum, for instance, of the distribution of the maximum, then p is 1/2. 1 minus p is also 1/2. The t is cancelled, and we get expectation of the maximum over 2. Yes.
So that PT is a lower bound of revenue, no?
Oh, it's equal, I think. Yeah, it's equal. Right?
You sell at T.
T is my price,
Okay, yes. Yeah.
and P is the probability that I sell at that price.
So the first thing is equalities.
Yeah, so the first thing here is an equality, yes. Good. So
Can you explain why you get rid of classes and then have
here,
max Vi minus t?
here this is just less. So yeah, this is like the maximum between this and 0, and this is just without the maximum between that and 0. Yeah. So, remember that what I want to prove in the end is that this is at least expectation of the maximum over 2. That's all I want to do. I'm not going to be able to prove something better than this. So long as I prove this, I should be happy. Okay, so there, and also t equals to the half of the expectation of the maximum gives me the same thing. So, very good. So why is this called balance prices? Because, you're basically balancing revenue and utility here. You are giving a price, T, that is high enough so that the revenue is significant, but also low enough, because if I put it just too high, basically I risk of just not selling the item by too much. And if I put it too low, then I will sell the item too quickly. And I cannot sell the item too quickly, because if I sell the item too quickly, I will miss people at the end, who might have like a very large contribution to the expectation of the maximum. So I need to leave enough probability of simply not selling.
I guess anything between these two values will work.
Anything between these values will work. Anything between these two values will work also. So there are a lot of possibilities that work, that give you the 1/2, but nothing gives you better than 1/2. Nice. So this idea has been extended in many directions. So one interesting example is matroids, but it's a more complicated algorithm. So they use this idea of balanced prices, but it's like a dynamic version of it. But like even if you go to online combinatorial auctions, and maybe this is something I want to mention. So online combinatorial auctions is like the same model, but now instead of selling just one ticket, I'm selling a set of items, okay? And then agents come, and instead of having just the random valuation for an item, they have a random valuation function for my sets of items, okay? So there is a huge family of possible valuation functions, and each agent picks one at random according to some distribution over these valuation functions, okay? Over all possible subsets, right? So yeah, exactly. And a random variable over these functions. So XOS valuations is a fairly large family, which you might not know. But Omar does know, no? So this is more general than submodular, but less general than subadditive. It's in between. Okay? So this is sometimes called fractionally subadditive. So it's a fairly fractionally subadditive is typically called also. I mean, Wikipedia page has the two names. Okay, so for this problem, you can actually extend the same balance prices idea. So you fix prices for each item, and you get the same profit inequality with the same factor. So you get that the assignment, the welfare of the assignment you collect is in expectation 1/2 of the welfare of the optimal assignment, where you know everything in advance and you solve this hard combinatorial problem. So that's probably like the largest extension of this. And it's not really true because there are other problems like matching, which are not in that family, but where, again, for matching, you can do very similar things. You can extend this idea in different directions. For subadditive, this is for subadditive, there is conjecture. It's conjecture to exist a constant factor approximation using just prices, but it's not known. So the best known is this log m profit inequality. But, sorry? Yeah. Okay, good. So that's conjectured to be possible, but we don't know. Anyhow, so there are many directions in which you can extend this idea. Quoi? Okay, so this is another. I can imagine, yeah. So this is another proof technique. So this is, consider the following problem. So it's completely unrelated. So if you didn't understand the last few slides, you can restart here. So now suppose I give you a sequence of Bernoulli random variables, okay? And these ones are either 1 or 0, of course, and they are 1 with probability xi, and we'll assume that the sum is 1. The sum is 1. We will observe these events one after the other, and we want an algorithm that selects a 1 with some high probability. Whenever there is a 1, so basically we want an online algorithm that condition on xi being equals to 1, it selects it with probability 1/2. That's the best possible we can do. You cannot be too greedy, again, we have the same issue, because if you select too quickly, it will happen that for late ones, we will never select them, or we will select them very rarely, conditioned on the fact that they are 1. So we want an algorithm that, even if it sees a 1, it skips this one with sufficient probability. Right? So think, I guess the easiest example is think of just 2 coins, just 2 random variables. The first one is 1 with probability 0.9 and 0 with probability 0.1. And the second one is 1 with probability 0.1 and 0 with probability 0.9. If you select the first one whenever it's a 1, then the probability that you actually go to the second stage is 0.1 only. Right? And therefore, condition on the second one being 1, you will pick it with probability at most 0.1. You cannot pick it more often than that. So that's not going to satisfy this property.
Sorry, but at each point you observe whether it's 1 or not, right?
Yes.
And you want to select 1.
You want to select a 1 only, yeah? You only want to select a 1, but you want the property that condition on any xi being equal to 1, you select it with probability 1/2. For any I, simultaneously for all i's. Right? So this is not so obvious how to do, but it can be done, and it can be done by somehow an algorithm with a recursive definition. So the algorithm, we will define it as follows. So if we get to stage I, and we see a 1, we take it with probability, so we take it or not. That's the only decision we can make, no? So we take it with probability 1/2 Ci, where Ci is the probability of reaching stage I. So the algorithm depends on itself, but in the past. So you can actually find all these Ci's. So with this property, you're done, and let me show you why. So first of all, the probability of reaching I plus 1 is this Ci plus 1, which we can compute easily as Ci times the probability that we don't take the I plus 1 guy, right? Which is, sorry, the ith guy. The ith guy, we take it with probability xi/2ci, so the product of these two things. So we don't take it with probability 1 minus that. So this is the probability that we reach stage I plus 1. And this gives you a recurrence. You solve it, and you get that Ci is equal to 1 minus the sum of the xi's, xj, of course, here, xj/2. Right? And this number, luckily, is between 1/2 and 1. So this is very important that it's between 1/2 and 1, because otherwise this is not even a probability. Okay? So first of all, this is a probability, and second, it's at least 1/2. Okay? So the probability that we take this guy is at least 1/2, and the algorithm is well defined.
So we only need sum of xi should be smaller than 1 for this algorithm to exist.
Sorry? We need?
Only need the sum of the xi should be smaller than 1.
Yes. That's the only thing we need, exactly. Yeah, and now the probability that you select, condition on this guy being 1, is 1/2 Ci times the probability of reaching that stage, which is Ci, so it's 1/2. Exactly 1/2. Sorry? Where? Yeah, xj, yeah. I already corrected it, but the screen didn't write. Yeah, xj, sure. Thank you. Good, so this is another proof technique. And how do we use it? Because we want to apply it to the same problem. So we go back to the profit inequality. Now we have this tool in mind, and we compute this xi star, the probability that Vi is the maximum of the valuations. Okay? So the sum of these guys is 1. No ties, remember this. Okay? The sum of these guys is 1. And and now we defined this, our Bernoulli random variables. And the Bernoulli random variable will be 1 if and only if Vi is in the top xi star quantile of its distribution. That's all. And now we applied our algorithm on this vi tilde instance, but we evaluate the revenue with respect to the original instance. Okay, so now what is the expectation of the algorithm? We condition again on which random variable we take. Remember that we take random variable I if with probability reaching the stage times the guy is 1 times our filter. Okay, so that's the probability that we actually take random variable I. So remember, Ci is the probability that we reach there. Xi star, this guy has to be 1. And this is the coin flip, the independent coin flip that we apply to this value of 1. Okay, so this here is Xi star over 2. And this is the value we get. This is the value we get. So the conditional expectation of Vi, given that is at least in the top Xi star quantile. Right? Good. So now we're done. So this here is 1/2 Xi star. And this is an event of probability Xi star, which is more, I mean, this conditional expectation is more than conditioning on any other event of probability Xi star, of the same probability. This is the best event of probability Xi star in which we can condition. And this here is just the expectation of the maximum times 1/2. Okay, so we have another proof using now a very different algorithm. Like, it's really a dynamic algorithm. And this idea of online contention resolution schemes has been also widely used in many settings. So there's a nice paper, a recent paper on like network revenue management kind of things, where you use this for matching and more like problems related to network revenue management. In Matroids, there are several versions of like selecting Matroids that, I mean, not in general Matroids, but for some specific Matroids, again, for matching, the balance prices idea gives some constant. Now we can actually improve using these more dynamic algorithms. You can get better results. And anyhow, there is a lot of work on this. When did I start actually? Do you remember?
Yes. So you have 25
Okay,
minutes.
good. Okay, so let me go to the next idea, which is the following. So we again have the same problem, exactly the same setting, but let's say now I don't tell you what the distributions are. And instead of telling you what the distributions are, I give you one sample from each distribution, just one. I give you one sample from F1, one from F2. Could be more, but let's say just one. Everything else is the same. Yeah, one sample is the same, no? Oh, okay, I don't know. I'm not a statistician, so maybe I'm, sorry?
A sample contains some number of draws.
Okay, a sample of size 1 then. Yeah. Okay, good, yeah. Yeah, so I tell you one value drawn according to this distribution, one value according to the second, and so on. Okay? So we know this theorem with full distributional knowledge. What is very interesting is that with one sample from each distribution, one draw for, I don't know, okay? I will maybe continue saying sample and then you translate it. No? Okay. You will correct me every time then. So with one, we again obtain the optimal profit inequality, the best possible profit inequality.
Without knowing the distribution.
Without knowing the distribution. I just give you a bunch of values. And I swear to God that these values are drawn from this distribution. Good. So
How do you do it? Sorry.
The expectation is going to be over the policy.
With the true distribution.
with respect to the true distributions.
The expectation is also over the samples.
No.
Just over
The expected value is the expected maximum VI. That's it. There are some distributions there, and that's where the profit is going to get the expected maximum valuation.
Just to say, next week, if for the students and if Alexei will follow, I don't know. So Jason Hartland will be giving a talk on options, and he will use property inequalities, and in particular this result, because sometimes if you do optimal auction without knowing the distribution, you can still use Myerson optimal auction and get 1/2 of the optimal revenue, even if you don't know the distribution. So there is a kind of robustness result.
Alexei, you had a question?
Yeah, how do you get it?
How do we get this?
With one sample.
Okay, we'll do it. We'll do it. Yeah, next slide. Yeah. Okay, so this is what I will actually do something more general. Okay, I will solve a more general problem than this, which I like it very much. So you then tell me if you like it or not. I will solve a game called the two-sided game of Google. So in the two-sided game of Google, I give an adversary n cards, and I ask you to write numbers on both sides, arbitrary numbers, whatever you want, on both sides of each card. Okay, so now I take all these cards, and we put one random side up on a table, like here, and the other side down. Okay, and my goal, so you wrote the numbers, and my goal is to take the largest value, the largest hidden value. So the process for doing this is I will flip the first card. Okay, I see a 0. There was an 11 here, but this guy is not playing anything. I should decide whether I take a 0 or not. Okay, then, let's say I don't take it. Then I flip again. I see a 5. I should decide whether I take it or not. Let's say I don't. Then I see a 26. And I decide whether to take it or not. Let's say I take it. So I got 26 here. Okay, this is a more general problem. Why? Because in particular, the adversary could write the numbers on the two sides of this card, of the first card, by drawing two draws, from F1. One is going to be the real value, the one that's behind, and the other is the sample, the one I'm seeing. Okay, then also in the second card, also on the third card, and so on. But now I am allowing the adversary to do whatever he wants, not only drawing these random values. So for anything, the adversary can do. So my objective is to maximize the expectation of the accepted value. The benchmark is comparing against the largest hidden value. The largest value that's not facing up, right?
Can you tell us again, like the numbers that you wrote on both sides? Did you use like random? Or?
Oh no, it's an adversary. I mean, it's not my fault. An adversary wrote this number.
You see on this side, like this.
You see some numbers here, and there are some numbers that are hidden.
How does it matter?
That's very cool, no? It's very cool. It does matter a lot because it gives you a lot of information about. I mean, what you know is that the side that's up is random. Okay, so the numbers that are behind are not arbitrary, right?
Why?
What is random?
The numbers, what's up, they're not related to the numbers there.
Well, I don't know, with probability 1/2,
So
it could have been the other way, right?
So the fact that we put them like this or like this is random.
Yes.
It's not the decision of the.
It's not a decision, right? I mean, of course.
It's not the
So,
decision
but think about the original problem again. You are putting here and there on the other side 2 random samples from the same distribution, right? So these 2 guys, I mean, I can swap them, and they are still 2 random samples from the same distribution, right? Okay, so here I'm just making it more general. I'm letting you write whatever you want. So if I can prove the same result for this more general setting, well, I also proved it for that.
Yes,
Right? But it's very important. If there are no, I mean, if you only write numbers on one side, and I cannot see anything, and I have to pick the maximum on the other side, I cannot do anything. There's no constant. If you do this, you can do 1/2. It's very different. Okay, very, very different. Good. Okay, so let's try to do it. I will give the idea only of the proof, but it's not very complicated. So let's do the, I mean, we have our pairs of numbers. Let me call them S1v1, S2v2, and so on, our pairs of numbers. And I will actually randomly assign them. Like, I will flip them at random, right? So I will say half of these guys are samples, half of these guys are real values. And I will say a random one of these two will be a sample, and a random one of these two will be a real value. And I will call A1 to A to n all the numbers that appear in decreasing order. Okay, I know nothing about this A1 to A to n. I know some of them, but I don't even know where they are.
Sorry, but what's the rule? How you pick? I still didn't get it. So 26, why you pick on the previous slide? The 26?
Sorry?
Oh, on the previous slide, why you pick 26?
Because I wanted to. There's no rule. It's an example. It doesn't matter.
Present the rule.
No, I haven't said anything about the rule. I mean, I did say it in the beginning. I will just take the maximum of the samples as the threshold. That's going to be my algorithm. I mentioned it. So I'm going to take the maximum of these guys, 20. That's going to be my threshold. And that's it. That's my algorithm. Very easy, right? So, okay, so you randomly shuffle here, and then we'll have some guys appearing on the sample part, and some of these pairs appearing on the real values, right? And now, I mean, think about it this way. So what is the probability that the maximum is A1? Omar, tell me, what is the probability that the maximum is A1? A1 is an arbitrary value, but what is the probability that the maximum is A1? Is 1 over, oh, no, wait. What I'm looking is at the maximum on this side. This is the maximum on the real values, right? So the probability that the maximum is A1 is just the probability that A1 is here, right? A1 was somewhere here with some other card, and I flipped them randomly. So with probability 1/2, A1 is here. With probability 1/2, A1 is here. Okay? So the probability that the maximum is A1 is 1/2. Good. What is the probability that my algorithm now picks 1/2? Picks A1, sorry, picks A1. Well, let me first do a slight trick. Let's say my algorithm will take as threshold the largest element here in L, and will always pick the smallest element in R that is larger than my threshold. This algorithm is always worse than my algorithm, right? Because normally my algorithm will just pick the first one that's above my threshold. I'm saying pick the smallest one above my threshold. That cannot be, I mean, that's worse than my algorithm. It's a lower bound on my algorithm. Okay, so now I take something here, something here is my threshold, and what I take here is the smallest guy larger than my threshold. Okay, so what is the probability that my algorithm gets A1 then? Well, first, of course, I need that A1 is here, because otherwise it's impossible to take it. And second, I need that A2 is here, because I'm going to take the largest thing bigger than A2. And what is this probability? Yeah, except if A1 and A2 are like on the same card, right? In which case it's 1/2. But generically it's 1/4. Oh, nice. So it's half the probability that the maximum is A1. And now, what is the probability that the maximum is A2? But the probability that the maximum is A2 is this guy is here, and this guy is here. So it's 1/4. What is the probability that I get A2? Well, I need that A1 is here, A2 is here, and A3 is here. So that's 1/8. So it's half of the probability that the maximum is getting a 2. And this is true for all a's. So I'm always getting half of the probability. I'm getting AI with half of the probability that the maximum gets AI. That's true for all a's. End of story. I mean, and there is an issue with the first time that you repeat a number. The first a that's repeated in a card, but it still works. I mean, you do the calculation there and it still works. So that's basically the proof. I can skip the proof now. Nice. And this idea is also very nice. So there are several, but maybe I should, I have only like 5 minutes or something, no? 10. Okay, so maybe I'll skip this. And let me show you the last idea, which is a new approach to the problem. So I started from the oldest proof to the sample proof is from 2020, and this is from, I don't know, from when. We'll see. 2026, hopefully, right? Maybe 2027, I don't know. Okay, so this is, it's very cute. So it's an idea based on differential equations, on ordinary differential equations. So again, we have our f's, and let me call f to the product distribution. So the distribution of the maximum, let me call it f, okay? And we can always bound everything by just rescaling and assume everything is supported in 0, 1. That's not. So without loss of generality, we can assume this. So the key idea here, I guess, is that we will fix a distribution of the maximum, and we'll look for the worst instance with that distribution of the maximum. Okay, the worst possible instance with that distribution of the maximum. And this worst possible instance turns out to be a Bernoulli kind of instance, a weighted Bernoulli kind of instance, in which we have random variables Vt, we take value t or 0, and take value t with probability, the difference, I mean, this is like the density times dt divided by the distribution.
So sorry, what is the problem here that you're solving?
Same problem, profit inequality.
With distributions, not with samples.
With distributions.
Okay.
We'll see what happens, but yes, with distributions. So this is the worst instance for a given distribution of the maximum.
Only for single threshold.
Yes, only for single, we don't know, but yes, only for single threshold. Okay, the worst instance for a given distribution of the maximum. Okay, so it's not very hard to prove, I mean, you do the math, it's relatively simple to prove that the distribution of the maximum of this instance is actually f, converges to f as dt goes to 0, of course, and that for any threshold algorithm, this gets worse than any other instance with the same distribution of the maximum. This gives you something worse. I mean, it's intuitively clear. These values are like increasing, and if you fix a threshold, you will just pick the first one that's non-zero. So if you have a different instance, you will improve a little bit.
And what does it mean, the worst instance?
The worst in the sense that the expectation of the maximum is constant, because I fixed f, and the single threshold algorithm gets as little as possible.
For all thresholds, algorithm gives as little as possible.
Right? So the ratio will be the largest. So the smallest, if you. Good. Okay, so now let v of t so be the expected value of threshold t in this instance. So our algorithm will just fix a threshold again, and we'll stop the first time one of these guys is above the threshold. Okay? So what is v of t going to get? What is v of t going to get? Well, your threshold was t. If exactly vt, the one corresponding to this same t, is not 0, then you get that. Then you get t. So what is this probability? Well, it's the difference of the f's here divided by the other, like exactly that. And then times the value. If that t is 0, then you get the same as if you would have played t plus dt. I mean, if that t is 0, then that t didn't appear, so you could have played t plus dt and get the same thing. So with this probability, you get t. With the complementary probability, you get v of t plus dt. And this gives you a differential equation for v, which you can easily write, and it's this differential equation. So v prime is v of t minus t times density divided by CDF. Okay? And v of 1 equals to 0. Remember that I'm assuming all the time that the support is 0, 1. Okay, very nice. So now we have a relatively simple ordinary differential equation. You can actually solve it explicitly. This is the solution. The optimality condition is that this is 1, this is maximized. This is a quasi-concave function. You can also prove this. It's not hard to prove that this is quasi-concave. It is maximized when this is true. Okay, so this is, the threshold is equal, the price that we set, I mean the threshold that you set, is equal to the value you get. That's something we observed before, and it's actually true for the optimal threshold. And this is the optimality condition, very simple optimality condition. Okay, so now we have a differential equation characterizing everything. And what's nice is that it gives a proof for basically all the algorithms we already covered. So let's see this. So first of all, you can, from there, you can not, I mean, it's fairly easy to prove that you satisfy this balanced prices lower bound. But what is more interesting is that you go to ChatGPT or Gemini and say, hey, we have this differential equation. Can you check whether t equals to f minus 1 of 1/2? So this is the median of the distribution of the maximum. Gives me the bound I want to, the 1/2 of the expectation bound. And then, yeah, it says, yeah, here is a short proof. And it's very easy, like the proofs that they give. So for both thresholds that we know, that we already showed, it gives the right inequality. And of course, anything in between also gives the right inequality, right? Why? Because it's quasi-concave. So we know that v of t is quasi-concave, right? So if you have 2 points that give something, anything in between get at least this something as well, right? So good. And also, I mean, this can also be done by ChatGPT, but then I didn't do it by ChatGPT. Like, I will not do it because I don't have time. But basically, you can very easily prove with this that if you take a random threshold according to the distribution, so according to the distribution of the maximum, which is our previous algorithm, you also get 1/2. Using the same, I mean, this proof here contains all the details of that, these 3 lines. So nice. So we have like one differential equation that encompasses all these proofs, all these proof techniques, and we don't know of applications yet because this is very new. But I hope that there are many. That would be my guess. And I hope people will use it to get new results and for different like combinatorial problems. One more thing which is nice is that, and this is, I guess, something that other methods do not get so easily, is that you can actually use it to quickly derive this difference profit inequality, which is an old result from the 80s or 90s. So basically now you have these random variables between 0 and 1, supported in 0, 1, and you want to bound the difference between the expectation of the maximum and the online algorithm. And this difference, you prove is at most 1/4, and this is optimal. This is best possible. Right? Good. So